back to another video. Today we will be talking all about 8086 assembly language, which is one of the core topics in my subject CS3101 that stands for Architecture and Organization with Assembly Language. So in this video, I will be explaining how 8086 assembly works by walking you through 4 different programming activities that we completed. So each activity demonstrates how low-level programming interacts directly with hardware, memory, and input-output devices. So specifically, I'll be discussing and explaining the following programs. The first is a program written in assembly language that creates a mirror effect of the screen. Then, a program that rotates the screen like a carousel. A program that accepts 2 5-digit inputs and performs addition. And finally, a program that allows the mouse to draw on the screen where pressing keyboard keys changes the drawing color. For example, 1 for green, 2 for red, and 3 for blue. So, by the end of the video, you will have better understanding of how 8086 assembly instructions manipulate memory, handle user input, and control screen output at a low level. So without further ado, let's get started. Now, let us start with the first program, which creates a mirror effect of the screen using our 8086 assembly language, which is the DOS box. So this program works by directly accessing the video memory and copying characters from the left side of the screen to the right side, making it look like the screen is being mirrored horizontally. So now, here is the set of code that will make the mirror. So, let's look at this line. This tells the assembler that the program starts at offset 100H, which is required for .com programs in the DOS. Next, we load 0B800H into the data segment register. This address points to the text mode video memory, where every character you see on the screen is stored. So each character on the screen uses 2 bytes, 1 byte for the character itself and 1 byte for the color or their attribute. Now we have this. This sets BX to 0, which means we start at row 0 or the top of the screen. Now we will enter the row loop. Inside of this loop, this program processes 1 row at a time. Now here's what's happening. Each row on the screen uses 160 bytes. That's because there are 80 columns and each column takes 2 bytes. So we multiply the row number by 160 to find the starting address of that row. So this result is stored in SI, which acts as the left pointer. Now, so SI moves from left to right and DI moves from right to left. So next would be the column counter setup, which is this one. This screen has 80 columns, but we only need to process half of them. So we set CX to 40, meaning the loop will run 40 times per row. Now we enter the call loop, known as the column loop. This will mirror characters. So now, inside of this loop, it will copy both the character and its color from the left side of the screen and places it on the right side. So this is the main step that creates the mirror effect. Next, we have this, called the moving pointers. Each move is by 2 bytes because one character uses 2 bytes. So, SI moves to the right to the next character, then DI moves left to the next character. Then, we'll go through this loop call loop, known as looping through the columns. This repeats the column loop until CX reaches 0. Now we'll be moving on to the next row. So after finishing one row, BX is increased to move to the next row, and there are 25 rows total. And if we are not done yet, the program loops back to process the next row. So from this, we're gonna be waiting for a key press. So like after all rows are mirrored, these two lines, this pauses the program and waits for any key press so we can see the result. And finally, this cleanly terminates the program and returns control to the DOS. So to summarize this, it cleanly terminates the program and returns control to the DOS in terms of this. So overall, this program directly accesses the video memory, and it uses two pointers to copy characters from left to right. So by doing this for every row, it will create a horizontal mirror effect on the screen. So now let us do the demonstration. This is DOSBox. So now I will change the directory to finals because that is where I saved my output. And then I have to type in this A86 mirrored ASM. Then in order to run this, I'll just type mirror already. And if I click enter, this side will be mirrored to the other side. So, ta-da! Voila! It's mirrored to the other side. Good as half. And that's all. Hello once again. Since we're already finished with the mirror, now let's move on to the second program, which creates a carousel or rotating effect on the screen using the 8086 assembly language. So this is the mirror one that we did earlier, and I will be doing the carousel. So this program works by shifting the characters in each row of the screen, making it look like the screen content is rotating continuously. So now let me explain the set of codes here. So first we have, First we have this. Here load 0B800H into the data segment register. This address represents the text mode video memory, where all characters and their colors in the screen are stored. So each character occupies 2 bytes, one for the character, one for the color attribute. Next, we're gonna be moving on to this one here. So this label, init loop, marks the start of the infinite loop. At the end of the program, it jumps back here, so the rotation keeps repeating forever, creating an animation effect. So now, inside of this loop, CX is set to 25, representing the 25 rows of the screen. DX is set to 0, which acts as the starting address of the current row. Next, we have our main loop. This loop processes one row at a time. So these 4 lines of code, what's happening is that DX points to the start of the current row, SI is moved to the last character of the row, then DI is moved to the second to the last character. So basically it's setting pointers for rotation, where this setup allows us to shift characters from left to right, like, you know, Now, oh no, what's this? Oh, there you go. My bad. Anyways. So this line is where the last character of the row is saved to AL. This is important because this character will later be placed at the beginning of the row, completing the rotation. Now we enter the inner loop. Inside of this loop, a character is copied from DI and then is moved from one position to the right into SI. So this shifts the characters one by one across the row. Now from here, moving the pointers. Both pointers move left, and each move is by 2 bytes because each character uses 2 bytes. Now, there's a condition here. This checks if SI is still within the current row. If yes, then the shifting continues. Now this, once the shifting is complete, the character saved earlier is placed at the start of the row. So this completes one rotation step for that row. And now this moves dx to the start of the next row, since each row occupies 160 bytes. And this line, this repeats the process until all 25 rows have been rotated. Now, from this, after all the rows are processed, this introduces a short delay, so the rotation is visible and smooth instead of instant. Finally, this one. This jumps back to the beginning, making the screen rotate continuously like a carousel. So like, basically from this, it goes left to right, from left to right. So to summarize, this program rotates each row of the screen. It shifts the character one position at a time. Then the last character is moved to the front. And then a delay creates a smooth animation effect. Now let us get this running. So since we have our previous one, which is the mirror, now we'll be doing the carousel, which I named the file loop. And now, here it is. Voila! You can see that. It loops infinitely. And in order to exit this, I just have to close this program. And that will be all for the second problem. Hello! Now let's move on to the third program, which allows the user to input 2 5-digit numbers and then adds them together using the 8086 assembly language. So this program performs the addition digit by digit, just like how we add numbers by hand, starting from the rightmost digit and carrying over when needed. Okay, so first we have these. Oops. These lines reserve 5 bytes of memory for each number, and each digit entered by the user is stored 1 character at a time. Now we have jump.start that skips over the function definitions and jumps directly to the main execution part of the program. Then moving on to the slow digits. This procedure reads 5 digits from the keyboard and stores them in memory. And here, CX is equals to 5, so we will read exactly 5 digits, and DI is equals to 0, so this indicates where digits are stored. Now from this, the DOS interrupts, so it waits for a key press, reads 1 character from all the keyboard, and it replaces in AL. So the character is stored in memory and DI moves to the next position. Now here in loop.load, this repeats until 5 digits are entered. Now we'll call that new line and ret. So basically a new line is printed and the program returns to the caller. Now here we have dot print digits. So basically this procedure prints the stored digits back to the screen. And following these 3 lines, basically this CX is equals to 5, that prints 5 characters, then AH is equals to 2, this is the DOS output function. Now, from this set of 3 lines here, each digit is moved into DL and then printed on the screen. After that, here we have this looked at print, called it new line, and read. So basically, all in all, this continues until all the digits are printed. So this one, a dot new line. From this until here, this prints a line, feed, and carriage return. So it's moving the cursor to the next line. Now here, add digits. This is the most important part of the program. You know why? Because CX is equals to 5. We're in 5 digits to add. DI is equals to 4. Start from the rightmost digit. Then BX is equals to 10, which stores the carry. Oh no, sorry. BX is equals to 10. That is used for division. Then DL is equals to 0. That stores the carry. Now, here in this part, in dot add, these lines load a digit from the first number, add the carry from the previous step. And then these add the digit from the second number and subtract 60H to convert ASCII digits into numbers. Now from here, this will divide the sum by 10. Then the quotient goes to AL, which is the carry, and then the remainder goes to AH, which is the digit. Now in here, this saves the carry for the next digit and then convert the result back to ASCII. Then it stores it in memory. Then after that, you move on to this one. This moves left and continues until all digits are added. So lastly, we have these. These prints the final carry, and if any, it will print the resulting 5-digit sum. Here, this is the main program execution. So these two, let I read the 5 first. What is wrong with my wording? Anyways, these reads the first 5-digit number. Then these 2 lines reads the second 5-digit number. Then I will call dot add digits, which will perform the addition and prints the result. Lastly, this will end the program and returns control to DOS. So in summary, this program reads 2 5-digit numbers, stores each digit individually, adds them digit by digit, handling carries, and finally prints the correct sum. So let's do a demonstration here. So here I have DOSBox. I'll now change my directory to finals, and now I will have to do, what's my file name? add.asm, because you know it's addition. And then when I do this, I have to input a 5-digit number. So let's try to add 90,000 by 90,000. What do I get? I will get 18,000. Now that one right there is basically the carry. Oh wait, my bad, sorry, it's 180,000, okay? So 90,000 plus 90,000 is equals to 180,000. And it works. Now let's try again. What if I add 000 and 000? You'll still result in 0. But why is there another 0 there? That's because it has 0 carry and it will include the carry there. Let's try one more thing. Let's do 11111 and then 11111. And I know the answer is 2. You know, like that. Did I say the exact number of 2? But anyways, here you go. As you can see, it's 22,222. Now there's a 0 at the left side because that's the carry. And since we don't have any carry, it's just 0. It's like 1 plus 1 is just 2 and there's no carry. Unlike here, 9 plus 9 is 18. So therefore, you'll have a carry, which is why there's a 1 at the left side. So that will be all for this demonstration for the third problem. Now we will proceed to the last one. Hello once again and welcome back to another video. Oh no, just kidding, this is the same video. So let's move on to the fourth and final program, which allows the user to draw on the screen using the mouse while changing colors using the keyboard. So in this program, the mouse is used to draw pixels. Pressing 1 draws in green, pressing 2 draws in red, then pressing 3 draws in blue. Then pressing the escape button exits the program. Now, we're gonna do the graphics mode. So here in this line, this indicates the program is a .com file. Then this switches the display into graphics mode 13H. So the mode 13H gives us 320 by 200 resolution, 256 colors, a linear video memory which makes drawing pixels easier. Next, here we load 0A000H into the extra segment register. This is the starting address of graphics video memory where each pixel corresponds to 1 byte. Now we will set the default color. So this sets the initial drawing color to green. The color value is stored in a memory variable called curcol. C-U-R-R-C-O-L. It's right here. Now, this is the main loop program. This loop runs continuously, allowing the user to draw and change colors in real time. So from this BIOS mouse interrupt retrieves BX, which is mouse button status, then the CX, which is the X coordinate, and DX, which is the Y coordinate. So now checking for left mouse click. So from this checks if the left mouse button is pressed. If not pressed, the program skips drawing and checks for the keyboard input. Now from this, the mouse cursor is temporarily hidden. This prevents color artifacts such as the cursor drawing unwanted colors on the screen. Now from here, this calculates the memory address of the pixel using the formula. So the offset is like Y by 320, then plus X. Yes, this one. Y times 320 plus X. So this tells the program exactly where to draw the pixel in the video memory. Now, from this, the current color is loaded and written directly into video memory, drawing 1 pixel on the screen. And then moving on to this one. The mouse cursor is made visible again. And then check keys. checking keyboard input. This checks if a key has been pressed. If not, the program loads back and continues drawing. Then this reads all the pressed key and store its ASCII value in AL. And from this, depending on the key pressed, 1 is green, 2 is red, and 3 is blue. Then if escape key is pressed, the program exits. Now here, this sets the color to green. Then here, this sets the color to red. Then this one sets the color to blue. Now here in the exit and restoring text mode, this restores the screen back to text mode. Then this cleanly exits the program and returns control to DOS. And this one here, which is the color variable declaration, curl call db0, this memory variable stores the currently selected drawing color. So overall, this program uses graphics mode 13H, the mouse is used to draw pixels, the keyboard changes drawing colors in real time, and the escape key safely exits the program. Now to demo it, A86 mouse.asm. Okay, so now I will type mouse. Okay, so here, if I click 1 and I have to draw, it's green. I can draw anywhere, it's green. And then if I click 2, then I actually drew red. And then if I click 3, I draw blue. Hello, so that's it for today's video. So to recap, we explored 8086 assembly language through 4 different programs, from creating mirror effect on the screen, to carousel style screen rotation, performing addition of 2 5-digit numbers, and finally a mouse drawing program with keyboard controlled colors. So basically these activities show how low-level programming works with memory, input devices, and graphics, giving us a deeper understanding of how computers operate at the hardware level. And I hope this video helped make 8086 assembly easier to understand and more interesting, especially for students taking the subject here in University of San Carlos, CS3101, Architecture, and our Organization with Assembly Language. Thank you so much for watching, and I hope you learned something from this presentation, and see you in the next one.